Hey everyone! Ever wonder how artificial intelligence can solve problems that even humans find tricky? Today, we're diving into a groundbreaking math paper that reveals how neural networks, those AI systems powering everything from voice assistants to self-driving cars, can approximate some of the most complex mathematical functions in existence. It's like teaching a computer to think like a mathematician, but with a twist. Let's start with a simple question. What does it mean to approximate a function? Imagine you're trying to predict the weather. You know the temperature, humidity, and wind speed at a bunch of points, but how do you turn that into a full forecast? A function is just a rule connecting inputs to outputs, right? But some functions are wildly complex, like the equations that describe shockwaves in a supernova or how a virus spreads through a population. These are partial differential equations, PDEs, and they're notoriously hard to solve. Here's the kicker. Neural networks can learn to approximate these solutions. The research shows that if you give a neural network enough layers and neurons, it can mimic the behavior of these complex functions with stunning accuracy. Think of it like a student learning to solve a difficult math problem by practicing similar ones. Over time, they get better and better. But how does this work in practice? Let's break it down. The paper uses a technique called function approximation, which is basically a fancy way of saying guessing the right answer based on patterns. They start by taking a function that's hard to solve directly, like the ones describing shockwaves or rarefaction waves, and then train a neural network to replicate its behavior. Here's where the math gets really cool. They prove that any function, no matter how wild, can be approximated by a neural network, as long as you give it enough parameters. It's like saying a painter can recreate any masterpiece if they have enough brushes and colors. The key is understanding how the network size, number of layers, neurons, etc., relates to how accurate it can be. But wait, there's a catch. Some functions are smoother than others. Think of a function as a mountain range. A smooth function is like a gentle hill, while a rough one is jagged and chaotic. The paper shows that smoother functions are easier to approximate, which makes sense. But even the most chaotic functions can be tackled with the right neural network setup. The researchers also tested different learning rules called loss functions. These are like the guidelines the network follows to improve. They compared two methods, one that worked great for sharp, sudden changes like a traffic jam, and another that handled gradual transitions like a slow-moving wave. The results? The right tool for the job made all the difference in accuracy. So why does this matter? Well, this math isn't just theoretical. It's the backbone of AI systems that model real-world phenomena, from climate change to financial markets. By understanding how neural networks approximate these functions, we're not just building smarter AI, we're unlocking new ways to solve problems that were once thought impossible. Now let's zoom in on the real breakthrough, physics-informed neural networks, PINNs. These aren't your average neural networks. They don't just memorize data, they embed the laws of physics directly into their calculations. Imagine a model that understands gravity, fluid dynamics, or thermodynamics without needing explicit grid-based simulations. This is a game changer for fields like aerospace engineering, where traditional methods struggle with discontinuities like shockwaves. But even PINNs have limits. Enter weak PINNs, wPINNs, the latest innovation. These networks are designed to handle weak solutions, mathematical answers that don't need to be perfectly smooth. Think of them like blurry movie frames that still tell the story. They're essential for hyperbolic equations, which describe systems with sudden jumps, like traffic bottlenecks or supernova explosions. How do wPINNs work? The team used Riemannian manifolds, curved, flexible spaces that can model everything from a sphere to a twisted, multi-dimensional shape. It's like giving the neural network a map of the problem's geometry, so it can navigate even the messiest scenarios. They also paired this with entropy solutions, a way to pick the right answer when multiple possibilities exist. Imagine trying to predict the future with multiple outcomes. Entropy conditions act like a rulebook to choose the physically meaningful one. Plus, they developed a new error analysis method called L1 contraction, which ensures errors shrink over time, even with jumps. This means the network doesn't just guess, it systematically improves, no matter how chaotic the physics get. The results? Their method matches the best possible error rates in math, proving it's super efficient. They tested it on real-world scenarios, like shockwaves on curved surfaces, and it nailed the predictions. This is a game changer for fields like climate modeling, aerospace engineering, and even medical imaging, where high-dimensional, complex systems are the norm. So what's next? This research shows AI isn't just crunching numbers, it's becoming a partner in solving nature's toughest puzzles. Whether it's predicting weather, designing better aircraft, or understanding the universe, these neural networks are opening doors we never thought possible. Thanks for watching. If you want to see how this applies to real AI systems, hit subscribe. Let me know in the comments what you'd like to explore next. Until then, keep curious. Rock it.